Hello, and welcome to this lesson on logarithms. Recall from a previous lesson, we learned about inverse functions. In particular, if we have a one-to-one function, then we learn how to find its inverse function. If we have the function y is equal to 3x plus 7, to find the inverse, we interchange the variables x and y, giving us x is equal to 3y plus 7. At this point, we would then solve the equation for y. Now let's apply this to exponential functions. If we have the function y is equal to 2 to the x power, to build the inverse, we interchange the variables x and y, giving us x is equal to 2 raised to the y exponent. At this point, we would solve for the variable y. To do this, we have to introduce the concept of logarithms. Rewriting the equation, x is equal to 2 to the y power, with logarithms would look like this. Y is equal to log base 2 of x. The previous two equations represent the exact same function, much in the same way that Professor Moore's name can be written Ronald Moore or Moore, Ronald. Two different ways to express the same name. Two ways to express the same function. Two ways to express the same name. So let's take a look at the definition of the logarithm. Y is equal to log base b of x means the same thing as b to the y exponent is equal to x. So example 1, convert the following into exponential notation. 4 is equal to log base 2 of x. Using the definition of logarithm above, we get 2 to the 4th power is equal to x. 2 to the 4th power will simplify. 2 to the 4th power is 16, which gives us x is equal to 16. Example number 2. Convert the following into exponential notation. 3 is equal to log base x of 64. Using the definition of logarithm, we get the following. X to the 3rd power is equal to 64. This one can also be simplified. Taking the cube root of both sides, I get the cube root of x cubed is equal to the cube root of 64, and the cube root of 64 gives me a 4, so I get x is equal to 4. Example number 3. Convert the following into exponential notation. X is equal to log base 3 of 81. Using the definition of the logarithm, we get 3 to the x is equal to 81. With these three examples, notice that the base number of the logarithm moves to the other side and becomes the base number of an exponential. The reason why is because logarithms and exponentials are inverses, opposites. So the base number of the logarithm, 3, moves to the other side and becomes the base number of an exponential. The base number of the logarithm, x, moves over to the other side and becomes the base number of an exponential. The base number of the logarithm 2 moves to the other side and becomes the base number of the exponential. So think about this with the following examples, opposites, inverses. If I have x minus 3 is equal to 8, that becomes x is equal to 8 plus 3. Subtraction on the left becomes addition on the right. They're opposites, they're inverses. So when you move it to the other side, you get the other one. Converting logarithms to exponentials is the same. When you move the base number to the other side, then the base number becomes an exponential. So your logarithms turn into exponentials, your exponentials turn into logarithms. Now let's go in the other direction, converting exponentials into logarithms. Convert the following exponential into a logarithm. 5 to the x power is equal to 7. Using the definition of logarithms, we get x is equal to log base 5 of 7. Example 5. Convert the following exponential into a logarithm. X to the 7th power is equal to 10. Using the definition of logarithms, that gives us 7 is equal to log base x of 10. Example number 6. Convert the following exponential into a logarithm. 4 to the 9th power is equal to x. Using the definition of logarithms, we get 9 is equal to log base 4 of x. Notice again, with these three examples, the base number of the exponential moves to the other side of the equation and becomes the base number of a logarithm. There are two common logarithms that are used, log base 10 and log base e. In fact, they are used so much that log base 10 is usually just written as log, L-O-G. So if you see log written without a base number, then the base is 10. Also, log base e. This is called the natural log and is usually written as ln. So if you see ln written, then it is base e, Euler's constant. Almost every scientific calculator will have an log button for log base 10 and an ln button for log base e. Some calculators have a button that can take the log of any base, but many do not. So what do we do if our calculator cannot calculate the log of any base? The answer is the change of base formula. With the change of base formula, we can change any base to any other base. So the change of base formula is this. Log base a of x is equal to log base b is my new base, log base b of x divided by log base b of a. So base a gets converted to base b. You can convert any base to any other base. For more practical versions of this formula, here's how the change of base formula converts to base 10. So log base a of x is equal to log of x divided by log of a. So this takes base a and converts it into base 10. We can also convert them into base e, the natural log. So log base a of x is equal to the natural log of x divided by the natural log of a. Let's take a look at some examples. Example 7. Use the change of base formula to change to base 10 and calculate the following logarithm. Round your answer to 4 decimal places. Log base 3 of 5. Solution. Log base 3 of 5 using the change of base formula, that's equal to log of 5 divided by log of 3. Using our calculator, we get 1.4650. Example 8. Use the change of base formula to change to base e, the natural log. Log base 3 of 5. Our solution, log base 3 of 5, that's equal to the natural log of 5 divided by the natural log of 3. Using our calculator, we get 1.4650. Let's take a look at the graph of logarithmic functions. The graph of the function f of x is equal to log base b of x, where the base number b is larger than 1, is this shape. This is the base graph for logarithms. They all have an x-intercept at the point 1, 0, and a vertical asymptote on the y-axis, which is x equal to 0. So let's take a look at shifts of logarithmic functions. The following are modifications to the logarithmic function that will shift the function either up or down. So if I have f of x equal to log base b of x plus 3, the plus 3 is not inside the logarithm, this will shift the logarithm function up by 3. If I have f of x is equal to log base b of x minus 5, the minus 5 is not inside the logarithm, this will shift the logarithmic function down by 5. The following modifications to the logarithmic function will shift the function either left or right. So f of x is equal to log base b, open parentheses, x plus 4, close parentheses. Notice the plus 4 is inside of my logarithm. This will shift the logarithmic function left by 4. Remember, your left-right shifts are backwards. Plus goes to the left, minus goes to the right. F of x is equal to log base b of, open parentheses, x minus 2, close parentheses, so the minus 2 is inside my logarithm. This will shift the logarithmic function right by 2. Reflections of logarithmic functions. The following modifications to logarithmic functions will reflect the function either across the x-axis or the y-axis. F of x is equal to log base b, open parentheses, negative x, close parentheses. So the negative is inside of my logarithm. This will flip the logarithmic function across the y-axis. F of x is equal to the negative of log base b of x, so the negative is outside the logarithm. This will flip the logarithmic function across the x-axis. All right, properties of exponents. So we got several properties of exponents. Property 1 says this: log base b of 1 is equal to 0. So what this effectively says is the log of 1, no matter what the base is equal to 0. Property number 2, log base b of b is equal to 1. So if the base number of your logarithm matches the number that you're taking the logarithm of, then it calculates to 1. So log base 3 of 3 would be 1, log base 4 of 4 would be 1, and so forth. Property 3, log base b of b to the x is equal to 1. So what we have here is an exponential inside of a logarithm. If an exponential is inside of a logarithm and the base numbers match up, then they cancel and we're left with just that exponent, just the x. Property 4, b raised to the exponent of log base b of x, all that is equal to x. So here we have a logarithm inside of an exponent. So if the logarithm is inside of an exponential and the base numbers match, then they cancel off and we're left with what's inside the logarithm. Property number 5. Log base b of u times v is equal to log base b of u plus log base b of v. So if we have things that are multiplied, factors that are inside of our logarithm, then we can break them apart using addition. Property number 6, log base b of u divided by v inside of my logarithm. This is equal to log base b of u minus log base b of v. So what this is saying is if we have a fraction inside of a logarithm, then we can break it apart with a subtraction. So it's going to be the log of my numerator minus the log of my denominator. And then our last property, property number 7, I have log base b of u raised to the n exponent. The difference between this and a property above is, notice the base number of the logarithm does not match the base number of the exponential. So I have log base b of u to the nth power. This is equal to n times log base b of u. So if we have an exponent on a factor inside a logarithm, then we can bring the exponent down in front and write it as a coefficient of the logarithm. So that exponent of n comes down in front, and I have that n as a coefficient now. So with these last three properties, let's take a look at how they're used to break down logarithms. Example number 9. Use the properties of logarithms to rewrite as the sum, difference, and integer multiples of logarithms. I have log base 3 of x cubed y to the 4th. All of that is over z to the 5th. So our solution. So using property 6 above, that's the one that had the fraction. So using property 6, we're going to get log base 3 of our numerator, which is x cubed y to the 4th, minus log base 3 of my denominator, which is z to the 5th. Using property 5, so property 5, that's one where I've got multiple things multiplied inside my logarithm. Using property 5, this then becomes log base 3 of x to the 3rd plus log base 3 of y to the 4th. So that logarithm that had the x cubed times the y to the 4th, that's now broken apart as two logarithms that are added. And then finally we have my minus log base 3 of z to the 5th. And then using our last property, where we take those exponents and move them down in front. So that's going to end up giving us 3 times log base 3 of x plus 4 times log base 3 of y minus 5 times log base 3 of z. So thank you for watching this lesson, and I will see you next time.